Hey everybody, and welcome back to Patel Academy. Today I wanted to cover the 2019 AP Chemistry Free Response questions in order to give you guys a sense of what type of questions might come on the upcoming AP exam, as well as go through some key problem-solving techniques, as well as some key concepts in order to help you guys better prepare for that. So let's get right into it with question number 1. Now I will try and follow the timed format of the free response questions. So the first 3 are about 23 minutes each, and then the last 4 are about 9 minutes each for a total of 1 hour and 45 minutes. So I'll try and finish the exam while explaining my content within this time. So for question number 1, we're talking about the compound urea. And question number 1a talks about the hybridization of the carbon in urea. So before I talk about exactly how the carbon in urea is hybridized, I wanted to go over briefly the technique that we can use in order to identify the hybridization of an atom within a molecule. So consider the molecule CH4, or methane. The trick behind identifying hybridization is to calculate the number of pi bonds. And so essentially you start at sp3, and for each pi bond you decrease the exponent or the number on p by 1. And so if you consider methane, each single bond has 1 sigma bond, so we have a total of 4 sigma bonds and 0 pi bonds. And so we consider this to be sp3 hybridized. On the other hand, if we consider something like ethene with a double bond, regardless of the carbon that you choose, you'll find that you get 3 sigma bonds and 1 pi bond, and so we have sp2. So if we consider urea, I'll draw just the carbon because that's what we're interested in. We have a double bonded oxygen and 2 nitrogens. And so when we look at this, I see 3 sigma bonds and 1 pi bond, and so similar to the above example, we have sp2 hybridization. So a very quick technique. While you have to be a little bit more careful at how exactly this works for higher levels of hybridization, such as sp3d or sp3d2, just keep in mind that the idea of counting pi bonds will work as long as you start from the top in those higher levels as well. So for these sp hybridized compounds, or within the sp range, you start at sp3 and you just keep decreasing 1 by 1 for the number of pi bonds. So to go sp3 to sp2 to sp if there's a triple bond. And of course, quadruple bonds, there's no hybridization for carbons. Alright, so that was question 1a. Moving on to question 1b, we see that we're talking about solubility, and I immediately see the word hydrogen bond. So what exactly is a hydrogen bond? Well, this is arguably one of the most important units in AP Chemistry is intermolecular forces, and hydrogen bonds are an example of that. So it's an IMF, or intermolecular force, between hydrogen obviously and either of the 3 most electronegative compounds, so F, O, or N. And so in this case, looking at the diagram, well, I see a couple of possibilities for H bonding using the definition above. Now keep in mind, for hydrogen bonding to occur, it's an attraction between H and either F, O, or N, but the H also has to be bonded to one of these elements. So if it was an H bonded to a C, there'd be no dipole over there in that bond, so it wouldn't be considered H bonding even if that H was attracted to another O, because there has to be a dipole on the molecule itself as well as an IMF attraction between 2 opposite molecules. So in this particular example, the H bonding can occur between the H of H2O and the O of urea, the H of H2O and the N of urea, or one that you may not have thought of, the O of H2O and the H of urea. And so either one of these would have worked. So I'll just draw a quick diagram. So let's say that our nitrogens are green, our carbon is black, our hydrogens are, let's say they're blue. And our oxygen, we can make it white. And then drawing the other water molecule. And so our hydrogen bond could be shown as such, that orange line. Any one of the above possibilities would be considered correct because you just had to draw one dashed line. Okay, so moving on to question number C. It says calculate the concentration of urea in moles per liter. Keep in mind that our concentration is the number of moles divided by the number of liters. Now, above we were given only information on mass and molar mass. So how exactly do we get moles? Well, we also have the formula N is equal to M, so our mass over the molar mass. And so in this case, it would be 5.39 divided by 60.06. And so plugging that into my calculator, I get 0.0897. moles. Now, if we consider our volume, well, it's 5 milliliters, but we have to convert that to liters, so it's 0.005 liters. And so our concentration is equal to 0.0897 moles per 0.005 liters, which is equal to 17.9487. Oh, sorry, 17.9487. I'm just going to use capital M. Molar or molarity, it represents moles per liter. It's just a shorthand notation. And so now remember, one of the most important things is to also consider significant digits. So if you look back into the question, the smallest amount of significant digits that we're given is 3. That's found in the grams measurement and the volume measurement. The molar mass was given to us with 4 significant digits, but we always choose the smallest one. So at 3 significant digits, we have 17.9. Molarity, or 17.9 moles per liter. Whichever format you choose, both of them are correct. Now, one of the things to think about is that I didn't do the traditional dimensional analysis. I will, however, include units here because I forgot to earlier. So including units is important, but you don't necessarily have to set everything up as one dimensional analysis problem. Why? Because sometimes if you make an error, it might be easier to check if you do each step on your own individually. However, if you do the traditional dimensional analysis way, don't worry, it's still accepted. It still works perfectly fine, especially to compare units. So whichever one you're comfortable with, both work. All right, so question number 1D. So 1D says that we have to identify whether the dissolution is endothermic or exothermic, and we have to use Le Chatelier's principle. So what is Le Chatelier's principle? Well, considering an equilibrium, a simplified equilibrium at least, where we have our reactants and our products in a reversible reaction. Le Chatelier's principle, or I'm just going to call it Le Chat, says that if there's some change to the reactants, in this case I'm going to say, let's say there's an increase in the concentration of reactants, then the system will respond essentially to alleviate the stress. So this change in the concentration of reactants, we call it the stress on the system, and Le Chatelier says that the system will respond in the opposite way of the stress. And so it'll cause an increase in products and decrease in reactants. Keep in mind, however, that we're not necessarily changing the equilibrium conditions, at least not without a drastic temperature change. And so because of that, the ratio between products and reactants will still be the same, even if the actual concentrations themselves are different. It's the ratio that we care about in equilibrium. And so while this one involves temperature, this particular scenario, the easiest way in order to sort through this and identify working backwards is to just look at what information we've given. So in this case, we have to use part C. This is important to recognize, is that we're going from 20 degrees to 25 degrees. And this change in temperature is directly associated to what we're trying to find out, whether it's endothermic or exothermic. So what we also know is that we went, using the value in the previous question, we went from 17.9 to 19.8 molar. Alright, so what can we do using this? Well, this increase in solubility, right? So I'm going to title this one, or it's fact number one. So using number one, up dissolution. So our increase in dissolution, what exactly does that mean? Well, it means that there was an increase in the product, right? Because we're essentially transferring, our product is just what's in the water. So what's aqueous? So that means that there's an increase in product. But what exactly happens with an increase in product? That means that there was a decrease in reactant. And this was our response. Keep in mind, we still have to do this in terms of the context of Le Chatelier. So we can call this decrease in reactant the response to the stress. Well, what stress exactly can cause a decrease in reactant? An increase in reactant, right? So this could be caused by an increase in the reactant. But in this case, because we can treat temperature as either a reactant or a product, we already know that what actually increased here is not necessarily the concentration of the reactant, but the temperature. And so, using Le Chatelier's, what can we say is that, so Le Chat proves the reaction is endothermic. Why? Well, you just go backwards. So you say that, okay, if I were to write out the actual response to this, I would provide a little bit more explanation in the end. I would say, so by Le Chatelier's principle, the dissolution in temperature is a stress or is a change in the reaction that is acted against by Le Chatelier's principle in response, causing a decrease in the reactants and thus an increase in the products, which indirectly causes an increase in the dissolution of urea. And that's visible through the increased solubility or the increased concentrations of the aqueous urea. So it's essentially just recognizing that you have to work backwards and use the information that you're given in order to connect all the dots. Alright, so moving on to question E. 1E is definitely a experimental question. So it is conceptual still, but it's more experimental based. It says that we have a ton of equipment and we're trying to identify the value of the molar heat of solution for urea. Knowing that the specific heat is 4.18, find out the specific measurements that are now required to be made. Now, in case if you didn't know, we are dissolving urea in water. And so this is just talk about the assumptions of calorimetry. We assume, unless explicitly stated, that the specific heat of the solution of any compound dissolved in water is the specific heat capacity of water. That's an assumption that we make. So this 4.18 was something that we would have assumed anyways if we weren't given that specific value. So we're given a lot of equipment, but keep in mind that the question is not asking about what equipment we need, it's the exact measurements that we need. And so just a quick recap, keep in mind that our delta H reaction is equal to our delta H divided by our moles of reaction. And delta H is technically plus or minus the absolute value of Q, depending on whether it's endothermic or exothermic. In this case, we've proven that it's endothermic, so it would be the positive absolute value of Q, which can further be simplified to MC delta T, and over the moles of reaction. Now, using this formula, we can easily identify what all stuff we need. So we need, to calculate the moles of reaction, we need the moles of both the reactants, so water and urea. And to calculate that, we need their masses. And the mass will also come into play in the Q. So for measurements, we need the mass of water, we need the mass of urea, and then we need our change in temperature. So we need our temperature, both initial and final. Now keep in mind that we do want to be specific, so don't just say we want our change in temperature, because that won't get you full credit. What will get you full credit though is saying that we want the initial temperature of the solution and the final temperature of the solution. So be explicit like that. So those are the 4 measurements. Now moving on to question 1F. Now we start moving into the other parts of thermodynamics, specifically entropy. So we're told that the change in entropy is 70.1 joules per mole Kelvin, and we're trying to identify the absolute entropy of urea. Now, just the definition of what a change in entropy is, well, our change in entropy of the solution, sorry, I'll write that better. Is equal to, well, what is delta? Delta is change, so it's S final minus S initial. But in the context of a chemical reaction, it's the S of products minus the S of reactants. And so, what are we given? Well, we're given that the total is 70.1. Trying to find some value X, and we're given this quantity is 104.6. So what is X? 174.7 joules per mole Kelvin. And that's your answer. So while this could explicitly be stated as a formula, this is just also the definition of what change means, or of what delta means. Alright, 1G. Using particle level reasoning, explain why delta S is positive for the dissolution of urea in water. Well, what exactly is delta S, or entropy? Well, we measure it as the disorder of a system. But we also know that entropy can be increased with up disorganization, although that is kind of a general term, and an increase in the molecular arrangements. Think about it. Molecules are, or at least electrons within an atom, are constantly moving around. Atoms oftentimes have slight motion as well. And so the more motion that there is, the more kinetic energy is developed, the more energy is lost as heat, and the increase in disorder, and thus the increase in entropy. And so, how exactly do we use particle level reasoning for this? Well, what can we say? We can say that if you consider the aqueous urea, so urea aqueous, well, in water, it's definitely more unorganized. Right? Because we all know that solids are definitely more rigidly packed and have stronger attractive forces compared to when they're in a liquid, because of an increase in heat causing some loss of attraction between adjacent molecules. And it's also up configurations or arrangements. And so because of that, we can say that, or I should say this is compared to solid urea. And so because of that, we can say that delta S must be positive. Simply because in a liquid, there's greater disorder, there's greater amount of arrangements for the molecules to conform to, and because of that, there's greater amount of disorder. So that's just using the definition of entropy. Final question in part 1, 1H. The student claims that delta S for the process contributes to the thermodynamic favorability of this dissolution. Support the student's claim using any data above. Alright, so thermodynamic favorability. Thermodynamic favorability. Now, how do we exactly quantify this? Well, we use delta G. And in terms of thermodynamics, delta G is equal to delta H minus T delta S. Alright, so using this last term, now we don't know much about delta H. We were told earlier that it's endothermic, and so delta H is going to be positive. We don't know how positive though, so we can't really make an assumption about that. What we can do though is consider the second term. Our T is going to be greater than 0 because T is measured in Kelvin in this case. We already have found out that our delta S is greater than 0. So this negative T delta S must be less than 0. Now what does this tell us? That delta G is small, because we have something being subtracted from a positive term. So delta G is going to be small, compared to if the entropy was negative, in which case we would have a larger delta G. So it's comparative. And so using that, we can say that because delta G is small, our reaction is favorable, thermodynamically of course, and so student is right. Technically by the definition of Gibbs free energy. So by the definition of Gibbs free energy, we take the enthalpy and we subtract it. We subtract from it the term temperature times entropy, and the definition of Gibbs free energy also tells us that a large delta G value is unfavorable, a small delta G value is favorable. An important thing to consider in this case is we don't get bogged down with a numerical value of delta G. You may think that with all the numbers you can calculate it. You can't, actually. It's supposed to be a conceptual question, and it's also not supposed to be overthought. That, oh, enthalpy is positive because it's endothermic, so there's no way that delta G is going to be less than 0. So because of that, I'm just going to assume that our delta H is going to be very large and that delta G is going to be positive. No, the question is not explicitly, but it's implying that you take it conceptually and don't overthink it. We want to just support the student's claim, so provide an explanation that can do so. That's it. Just answer the question and get it over with. Alright, question number 2. This one is a little bit more focused on atomic structure. So, question 2a asks us about the molecule with the largest bond length. Now, these are all diatomic molecules, and so remember that our bond length can be defined as the distance between the nuclei for our purposes. And so, if you consider the periodic table, I'll just draw the one group that I need. Split it into its parts. I see that fluorine is going to be on top, then chlorine, then bromine, then iodine. And so, if you recall the trend of the periodic table for atomic radius, as you go down, my radius increases. So I has the greatest radius, and thus I2 has the largest bond length. And so the answer that you should circle should be I2. And where it says to justify your answer in terms of atomic structure, say that because I has the largest atomic radius, the bond length of I2 is going to be larger than any of the other diatomic molecules. Alright, question 2b. So using the data in the table above, write the balanced equation for the thermodynamically favorable reaction that will produce Br2 when the teacher combines two of the reagents. Justify that the reaction is thermodynamically favorable by calculating the value of E for the reaction. Alright, so now we're throwing in some electrochemistry into it. So what exactly defines thermodynamically favorable electrochemical reaction? Well, similar to how we want to minimize delta G, we want to not necessarily maximize, but our E value, our voltage, has to be greater than 0. And so E being our cell potential for an electrochemical cell made up of these half reactions. And so think about, well, okay, we want to make Br2, so we know that we have to have that first half reaction flipped over. So we have to have 2Br minus going towards Br2 plus 2E minus, and now our voltage would be negative 1.07 volts. And then think about what would allow us to have a positive E value or cell potential. Well, if we include chlorine, right? Because then we have Cl2 plus 2E minus goes to 2Cl minus with 1.36 volts. And so combining them together, we get Cl2 plus 2Br minus forms 2Cl minus plus Br2, and our cell voltage is going to be positive 0.29 volts, I believe. And so, yes, I believe I did that math right. And because our E is positive, so if it's greater than 0, we prove that it's favorable with these two half reactions above. All right. Question C says that the boiling point of Br2 is 332 K, and the boiling point of BrCl is 278 K. Explain this difference in boiling point in terms of all the intermolecular forces present between molecules of each substance. Alright, so here's where it gets a little bit tricky, because a lot of these times what happens is students just memorize the priority of the intermolecular forces without actually considering what might happen in context of the question. Or they get really confused because they've just memorized. So 2C. Sorry. So our molecule Br2, so I'm going to write Br, we have lone pairs. Our bromine molecule has only London dispersion forces, because if you have two of the same molecules bound together, their electronegativity is 0, and so if I create, I'll just create a chart actually. So I'll draw my BRCl. And so if you consider BRCl versus BR2, well, in BR2 we only have LDFs. So recall, our London dispersion forces are the forces present in all molecules caused by the shifting of the electron cloud, which causes minuscule and momentary electronegativity shifts in the molecule. They're constantly changing and they're very, very weak. Keep that in mind. BRCl has LDF, obviously, but if you consider the electronegativity as well, you'll see that there is actually dipole-dipole forces. So I'll say dip, dip. And so what you might think is that, okay, well, why does BRCl have a lower boiling point if it has the stronger IMF? Well, here's where students often got bogged down, and here's where you need to be careful, is that even though there is an increase IMF because of the dipole-dipole, it may not be enough to overcome or to become larger than the LDF forces within the BR2 molecule. And so that's what you need to consider, is that the LDF in BR2 is greater than LDF plus dipole of BRCl. It doesn't ask you to explain why necessarily, it just says that explain the difference. The reason why is because the intermolecular forces of the bromine molecule, the bromine gas molecule in this case, no, the bromine solid molecule in this case, is greater than the combined IMFs of BRCl. And therefore, the BP of BR2 is greater than the BP of BRCl. Alright, so that was just a simple conceptual problem. Number D. Alright, so it says calculate the pressure in the container before equilibrium is established. We're given a 0.1 mole sample of pure BRCl, and it's put in a 2-liter container at 298 Kelvin. Alright, so how do we do something like this? Well, ideal gas law is going to be our best friend in this case. So what is the ideal gas law? Well, PV is equal to nRT. So we're solving for P. So P is equal to nRT over V. Keep in mind that our N is M, our mass over our molar mass, so we can also simplify this as mRT over mV. And so our mass is, oh sorry, never mind, we're given the moles. So we don't actually need this. Usually sometimes you're given the mass, so I just defaulted to writing that expression, but in this case they were generous. So 0.100 moles times the gas constant. Keep in mind, we're used to seeing the atmospheric gas constant. So not in some other things you may have seen like kilopascals, but it's 0.08206. I'm running out of room, so I'm not going to write the units, but on the actual AP exam, I would suggest that you write the units for everything times the temperature, 298 Kelvin, because we are at, it gives us 298 Kelvin. If it was Celsius, keep in mind the conversion that you would have to do in this case, because our gas constant has Kelvin in it, and then divided by our value, 2 liters. So plugging that into a calculator, you get, when you convert significant digits, 1.22 ATM. Now, I did write 2 liters. I'm actually going to change that because they gave us 2 2.00. So better to state it as it is in the question so you don't mess up your significant digit. So the smallest amount that we have right now is 3, so that's what we're going to use. All right. Question E says, write the expression for the equilibrium constant for the decomposition of BrCl. Now this one I'm just going to do on this same slide because it's a very quick and short question. Keep in mind that our K, now we could do partial pressures in this case because we are working with gases, but I've always just defaulted to using concentration. It's easier than partial pressures in my opinion. So remember, it's the concentration of product to its exponent divided by the concentration of, the reactants to its exponents. So our expression here would be Br2 Cl2 over BrCl squared. Keep in mind that these are all concentrations, but if you did write this in terms of partial pressures to do later questions, that would be completely fine. Alright, so that was E. Moving on to F. We are given the fact that 42% of the original compound has decomposed. So determine the value of K for the decomposition reaction at 298 Kelvin. All right, our best friend, ice tables, or as I like to call them, rice tables. The traditional way is ice tables. I say rice tables because of the reaction that you write at the top. I write it as a reaction instead of just at the individual components. Makes it a little bit easier. So our reaction is 2BrCl goes to Br2 plus Cl2. Okay. So in terms of our initial concentrations, what are we given? Well, we're given that our BrCl is 0.1 we're given that we have 0.1 moles of this sample and it's placed in a 2-liter container. And so what we can get is 0.1 moles divided by 2 liters, so 0.05 molarity. The question also says, keep in mind this wording, previously evacuated rigid container. So these are both 0. And then think about our concentration. Well, here we're going to be subtracting 2 times some quantity. Each of these we're going to be adding some quantity, right? But then what you also have to consider is while these expressions are in terms of x, we do have a way of figuring out what x is, namely the fact that 42% of the original sample has decomposed. And so what that tells us is our concentration of BrCl that's decomposed is equal to 42% or 0.42 times our original value, which is 0.05. And so 0.42 times 0.05 is equal to 0.021. Keep in mind this is still moles. And so our change, so this is our change. And so our change of BrCl is 2x. So if 2x is equal to 0.021, x is equal to 0.0105 approximately. These values I'm just going to leave in my calculator to use. And so our K is going to be 0.0105 times 0.0105 divided by 0.05 minus 2 times 0.0105. This is just me substituting for x. And then as I calculate this, 0.0105 squared divided by 0.05 minus 2 times 0.0105. And I get, sorry, let me just check this really quick. Oh, sorry, the denominator is squared. I forgot. As we found out in our previous question, the denominator is squared because it's 2 BRCL. And so, let me do that calculation. I knew there's something a little bit off because of the number. And 0.05 minus 2 times 0.0105 squared. Alright, that's more accurate. I get 0.131. And then I'm going to, based on significant digits, round this to 0.13. Now keep in mind that K equilibrium, or KC, however you address it, or KP, is unitless. So the answer is just 0.13. Alright, so that was a nice table. Those kind of equilibrium questions are a little bit longer, but still manageable. And then 2G, wow, that was a big 2. Calculate the bond energy of the BRCL bond in kg per mole using the delta H for the reaction, which we're given is 1.6 kilojoules per mole reaction, and the information in the following table. Alright, so keep in mind one of the definitions of our delta H is equal to the sum of bonds broken keep in mind these are energies minus the sum of bonds formed. Alright, and so we also have to consider the amount of bonds. So we should technically multiply by the number of moles. I'm not explicitly writing it in here, but I will be doing that. And so think about what's broken. Well, our BRCL is broken. So I have 2 of these BRCL bonds broken. And then minus, well, I have 1 BRBR formed plus 1 ClCl formed. And so if we just plug in the information, we're given that this is 1.6 kilojoules per mole is equal to 2 times X minus 193 plus 243. Doing the math quickly in the calculator, you should get an X value of, I believe it's 219. Let me check. Plus 193 plus 243 divided by 2. I get 218.8. And then, of course, once again, always remember your significant digits. So it's about 219. And that marks the end of question number 2. Moving on to question number 3. This is the last long answer. Let's check the time. So each question was supposed to be about 23 minutes. We're currently at 44 minutes, so just a little bit before the 46-minute cutoff. So that means that we're making good time. Oops. So question 3A. Write the net ionic equation for the reaction that occurs when these two solutions are mixed. Alright, so net ionic equation automatically means you just consider the precipitate. And so this is a very free question. Our precipitate is calcium carbonate. And so our calcium ion is Ca2+. Our carbonate ion is CO3 2-. I should also probably include AQ. Forms CaCO3 as a solid. It's a very simple equation, so it's fairly free points. Just keep in mind that you need to include the charges and you need to include the states for getting full marks. Alright, so our next question says that the diagram below is incomplete. Drawing the species needed to accurately represent the major ionic species remaining in the solution after the reaction has been completed. Okay. So I'm going to also just do this right here. So this is an A, by the way, not a D. So 3B. I'm going to draw my beaker. I'm going to draw the existing ions in red, and the new ones I will draw in a different color, probably white. Alright, and so what exactly do we need to do over here? Well, what we are told is that, so we're trying to find the major ionic species remaining after the reaction has been completed. So we start off with Na2CO3 and calcium nitrate, and we form 2 NaNO3 and calcium carbonate. Keep in mind the quantities. So what do we notice here? Well, in our beaker we have 2 sodium ions. If you look at the formula for sodium carbonate, every 2 sodium ions corresponds with 1 carbonate ion. So 1 carbonate ion requires 1 calcium ion in order to precipitate. So assuming that there's no carbonates left, we only had 1 to start off with, which means that we only required 1 calcium. Alright, what's left? Well, for every 2 nitrates, we require 1 calcium, but there's 4 nitrates left, right? And so because there's 4 nitrates left, there should have been 2 calciums. But we've only accounted for 1 calcium to precipitate. And so the answer, by our deduction, has to be our Ca2+ ion. And so that's the answer to this question. So this is just an idea of, do you understand how reactions work? And it's just a fun little question to do, I guess, in terms of counting and making sure that all the numbers stoichiometrically match. I guess it's a test of, do you understand how stoichiometry works? 3C. Determine the number of moles of Na2CO3 in the original 50 ml solution, given that we dried the precipitate of calcium carbonate and got the data in that table. Alright, so what are we told? Well, we are told that we have 0.93 grams of precipitate. What else are we told? The molar mass of the precipitate is 101. So I immediately use my formula, N is equal to M over M. And I get 0.93 grams divided by 101 grams per mole, and I get 0.93 over 100.1, 0.00929. moles. Makes sense considering how you're basically dividing by 100, so you just shift the decimal 2 over. Now what else do we know? Well, we know that for each, if we look back at our equation, for each mole of calcium carbonate that we had, we require 1 mole of sodium carbonate, Na2CO3. So using our stoichiometry for that, I'll scroll back down to where we were. We require, because it's a 1-to-1 ratio, now you could do this stoichiometrically using dimensional analysis, 0.00929 moles of Na2CO3. So this was just recognizing that there's a stoichiometric relationship between all the reactants and products, identifying what that is, and using one given to solve for the other ones. The rest of the table hasn't mattered yet, however, it might matter in future questions, so that's probably why they provided it. Alright, It was a short question, so I'll just do D on here as well. The student realizes that the precipitate was not completely dried and claims that as a result, the calculated Na2CO3 molarity is too low. Do you agree with the student's claim? Justify your answer. Okay, so let's think about this. The water, so if it hasn't completely dried, there's water in it. However, we're not accounting for that water in our molar mass. So think about where the mass and the molar mass is when we're calculating the number of moles. Mass is on top, molar mass is on bottom. So if we're increasing our numerator of a fraction, the overall value of the fraction is going to go up, which means that by presence of water, the number of moles of CO3 will increase, and thus, or sorry, I shouldn't say will increase, I just say will be higher. And thus, number of moles of Na2CO3, because the stoichiometry remains the same, will be higher. The stoichiometry isn't affected, molar mass isn't affected, only the mass is, and that'll cause an increase. And thus, I disagree with the student. Alright, 3E now. Alright, so after the precipitate forms and is filtered, the liquid that passed through the filter is tested to see if it can conduct electricity. What would be observed? Just a fair answer. Well, we already see that there are going to be ions in the solution. Which will allow for electrical conductivity. That's just the idea of an ion. It has a charge on it. Remember, electrical conductivity is just a flow of electrons, and a charge will cause a flow of electrons, either through attraction or through repulsion. And so we can say specifically the ions that are going to be left are Na plus and NO3 minus. And then if you look back on the diagram, you wouldn't be wrong to actually say Ca2 plus as well. Because technically, while it wouldn't exist, it is possible based on that particular configuration that there is an extra calcium ion, and so you're not wrong if you were to state that one as well. It's not necessarily, but again, you aren't wrong. Sorry, let me see how big this question is. Alright, I think we can do 3F over here as well. Alright, so number I. We want to try and find out, so now we're moving into the equilibrium thing. So it is, in this case we're using our sodium carbonate and adding it to water in order to get hydrogen carbonate, the ion, as well as, or I guess the bicarbonate ion, and then a hydroxide ion. And then we're given a Kb expression, and its value is 2.1 times 10 to the negative 4. We want to try and find the OH in the solution. So identify a laboratory method, not titration, that the student could use to collect data to determine our hydroxide concentration. Well, isn't this a great question? Because they've explicitly said not titration, and usually students will default to titration or redox titration, depending on the scenario, whenever they see a lab method, because of how common it is. So what exactly can we do in the lab? Well, does it really need to be complicated? Just think about that. Does it really need to be complicated? No. What exactly can we use the concentration of OH for? Well, concentration of OH is related to POH. And we also know that POH plus pH equals 14, right? At least for standard conditions. And so what we can do is we can just write it in white. We can just measure pH. It's that simple. So no need to overcomplicate things, no need to come up with some elaborate procedure to identify and like isolate the hydroxide from the bicarbonate ions, then calculate like the density or something. Don't go that extreme. All you need to do is measure the pH. Now explain how the student could use the measured value of our hydroxide to calculate the initial concentration of our carbonate ion. Okay, do not do any numerical calculations. Well, it says not to. I'm actually going to switch to the next page looking at this question. Just because even though it did say to not do any mathematical calculations, it did say to set anything that we can't set one up. And that's probably the easiest thing to do over here. So just like titrations are the best friend of acids and bases, the ice or rice table is our best friend for equilibrium questions. So let's see. If we consider our ice, and then, the imaginary rice component as well, we have CO3 2-. I'm not going to include the water because it wouldn't be included in our K expression anyways. So I'm not going to fill out its rows. I'll still include it for completion in the reaction. So this forms HCO3 OH-. All right. So we got our R figured out in the rice. Now explain how we could use the measured value to calculate the initial concentration. Okay, well, if we don't have our initial concentration, this time, because X is commonly used in the change, I'm going to call it Y. This is going to go minus X. I'm just going to say Na, Na, Na. So this is going to be Y minus X. This is going to start at 0 because we're dissolving it in water, so there's none of these ions previously. We're going to add X, and so we're going to be left with this. And so our Kb expression is going to be equal to X squared over Y minus X, and this is equal to 2.1 times 10 to the negative 4. So what you would say in your explanation is that you can identify what the final concentration of OH is, and you can solve for Y. Now, if you wanted to, you could do some rearranging in order to make this a little bit easier. So I'm going to say that Y minus X times Kb is equal to X squared. So Y is equal to X squared over Kb plus X. And so you just have to substitute your X. You could even plug in 2.1 times 10 to the negative 4 for Kb and say just find and plug in X. But essentially, setting up the ice table or rice table is your best bet over here. Just we don't plug in values. That's all that means. But you still have to go through this process. Looking at 3G now. This is the final long question, by the way, so that's nice. In the original Na2CO3 solution at equilibrium, is the concentration of HCO3 greater than, less than, or equal to the concentration of CO3? Justify your answer. Now these are the types of conceptual questions where you have to interpret some value without mathematics, and these are quite common now in the AP exam. So if you consider at equilibrium, well, our Kb is 2.1 times 10 to the negative 4, which is less than 0. So because of that, our concentration of products is less than our concentration of reactants, and so our concentration of HCO3 has to be less than our concentration initially of CO3. because KB is less than 0. Okay, and then going on to 3H, the student needs to make a carbonate and bicarbonate buffer. Is the Na2CO3 solution suitable for making a buffer with pH of 6? Okay, how do we do this? Well, we're given the Kb is equal to 2.1 times 10 to the negative 4. Remember, when we're working with buffers, if you think back to the Henderson-Hasselbalch equation, we consider pKa and pKb, right? So I'm going to calculate my pKb value here. Alright, so we take the negative log of 2.1 times 10 to the power of negative 4. I get 3.6. 7, 8, if I round. And so the resultant, my pKa, is equal to 14 minus 3.678. Now you could make a conclusion from pKb, except usually students are more adjusted or more used to concluding from pKa directly. So my pKa is going to be 10.322. And so because my pKa is not equal to my pH, it's not even close, to be exact, this is not a good buffer. So all you have to do is remember that you want to try and make your pKa close to your pH. Now, if you think about the Henderson-Hasselbalch equation, the idea is that your pH is equal to your pKa plus your log of your ratio between your two parts of the buffer, but you want to try and make the two parts equivalent to where there's a high amount of resistance of a pH increase or decrease. And when there's the maximum amount of resistance in the buffer is when the concentrations of the two conjugate acids and bases are equivalent. So if you think about it, if the concentration of CO3 and the concentration of HCO3 are equivalent, then their ratio is going to be 1. The log of anything is the log of 1 is always going to be 0, and so your pH is going to be equivalent to your pKa. Because there's such a large difference here, there's very minimal strength within the buffer in terms of resistance of both in pH increase or decrease, and that's why conceptually it's not a good buffer. So understanding that principle is important. Alright, so that marks the end of the long free response questions. Now, I've been recording for 1 hour and 3 minutes now, and the recommended time was 1 hour and 9 minutes, I believe, so we definitely are making really good time. We're just a little bit ahead, which is perfect almost, because you really only need about 5 to 10 minutes at the end just to check over your work quickly, so this should give enough time. Alright, 4A, describe the effect of raising the temperature on the motion of CO2 molecules. Well, this is just using the molecular gas theory, or you can even consider it in terms of kinetic energy. So up temperature is equal to up KE, which is equal to up speed. And then I would just say by the molecular gas theory. Alright, that was question A. Very, very straightforward. Most probably just a 1-point question because of how straightforward it is. I would, however, convert this relationship into a sentence form just to be more professional on a test. Calculate the pressure of the CO2 in the container at 425 Kelvin. Think about your gas laws. You have Boyle's law, you have Charles' law, you have Gay-Lussac's law. Our values are relating pressure and temperature, so keep in mind that our law is going to be P1 over T1 is equal to P2 over T2. You could also derive this from the combined gas law, which is that P1V1 over T1 equals P2V2 over T2, and both the volumes are the same, so they'll cancel out. Our initial pressure is going to be 0.70 divided by 299. That's equal to our X over 425. So our X value is going to be 0.99. Our units are going to be atmospheres. Once again, another straightforward question. If you guys do want a refresher on gas laws, keep in mind that basically what the gas laws are saying is that the three quantities, pressure, volume, and temperature, are proportional to each other, either directly or inversely, depending on what two quantities you're comparing. You can also see this in the ideal gas law. PV equals nRT. If you consider the P and V, they're on the same side, so you can consider them as being directly proportional, while P and T are on opposite sides, they're inversely proportional. Okay, so question number C. In terms of kinetic molecular theory, or the molecular gas theory, briefly explain why the pressure of the CO2 gas in the container changes as it is heated to 425 Kelvin. Okay, this one, if you've taken a little bit of physics, might help. What exactly is pressure? Pressure is the force per area. It's measured in newtons per meter squared. So my increase in temperature causes increased movement, which causes an increase in the number of collisions. And these collisions occur with increased energy, which is increased amount of force per unit area, depending on what you define that to be, and thus it's an increase in the pressure. Just a lot of logical connected statements. You should probably, once again, write that out a little bit more. So I would say something like faster moving gas particles, or an increase in temperature causes an increase in kinetic energy, and thus the faster moving gas particles collide more frequently with more energy, and thus the force per unit area is increased, which increases the pressure. Alright, and now 4D. The student measures the actual pressure of the CO2 in the container and observes that it is less than the pressure predicted by the ideal gas law. Explain. Okay, so there are a couple of reasons. Number one, there's attractive forces. Which cause down pressure. And then one of the other ones is their inelastic collisions. I'm not going to go through all the physics of this, but essentially with both of these points, what happens is inelastic collisions means that there's a loss of energy, which occurs in most realistic collisions. And so because of that, because of the loss of energy, most probably to heat, we don't have the same amount of force and thus the same amount of pressure. So essentially all you really need to do is just consider what can actually be affected. So when you're using the ideal gas law, you have a pressure, your volume isn't going to change, that's going to stay the same. Number of moles is just how much you put in initially. The gas constant is a constant, it isn't going to change, and your temperature isn't going to change. So the only thing that could really be affected is pressure. Now how is pressure affected? By a change in force. So what could cause a change in force a little bit lower than what you'd predict optimally? Well, a loss of energy causes a loss of force, or extra forces that negate existing forces. So that's essentially why 1 and 2 work. Alright, number 5. This is photoelectron spectroscopy. A fun topic. PES. Alright, so based on the spectrum, write the ground state electron configuration of the element and identify the element. Okay, how exactly do we do this? Well, we look at the peaks, alright, and we assume that the graph has a scale of 2, 4, and 6. Why? Well, because our first subshell, right, so our 1s subshell can only contain 2 electrons. And so as soon as you move past that, the peak of the 1s electron, you know, represents 2. Now, our 2s can only hold 2 electrons, but our 2p can hold 6. And so if you move past the 2p, then the peak of that has to be 6. And so what do we get? Well, this first peak is going to represent 1s2. Our second one is going to be our 2s2. Our third one is going to be our 2p6. This fourth peak at 7.1 times 10 to the negative 18 is going to be 3s2. Then we're going to have 3p6, and then we're going to have 4s2. Keep in mind that 4s2 comes before our 3d, so this would be incorrectly labeled as 3d2. You have to include the 4s2 first. And so identifying the element, well, if we start off on row 4, on period 4, and if we look exactly at what element occurs, or you can count the number of electrons. So 2 plus 2 is 4, plus 6 is 10, then 12, then 18, then 20. Well, what atom or what element has 20 electrons? Well, you guessed it, it's calcium. Alright, so that's 1 and 2. B, we get into some modern chemistry or quantum chemistry to calculate the wavelength in meters of electromagnetic radiation needed to remove an electron from the valence shell of an atom in the element. Alright, so keep in mind that our energy is equal to, based on our formula sheet, it's Planck's constant times V, so V is the frequency. We can also express V as being C over lambda. So it's Planck's constant times C over lambda. Lambda here being the wavelength. Alright, and so what do we get? Well, we get lambda is equal to Planck's constant times C over E. Plugging our values in, we know that Planck's constant is 6.626 times 10 to the negative 34. This is measured in joule seconds times the speed of light, so 2.998 times 10 to the 8th. This is in meters per second. And then our valence energy is going to be this last peak, so the 6th peak. The energy on the PES is the binding energy. We need to break exactly that binding energy in order to extract a single electron from that subshell. So it's going to be 0.98 times 10 to the negative 18 joules. Do not get confused and make it your first peak, the 647. That would be incorrect. The valence is going to be the outermost on a PES, or a photoelectron spectrum. And so calculating our wavelength, we get 2.03 times 10 to the negative 7. And our wavelength is going to be measured in meters. So a little bit of quantum chemistry right there. They like to throw that in sometimes just to make sure that you haven't skipped it because of how short of a unit it is at the AP level. Alright, question number 6. So we're almost actually finished. So we're talking about nitrogen dioxide. I'm given 3 graphs. Now, even though the question says it, you should recognize that I have a graph of concentration against time, 1 over concentration against time, and ln of concentration against time. Now, what exactly does this mean? Well, so I write down that this is talking about 6a. So 6a says, explain how the graphs indicate that the reaction is second order. Well, if you think about your rate laws, think about exactly what is in each rate law, right? So we have our first order, our 0 order, first order, and second order. And so recall that for a zero order rate law or a zeroth order reaction, the rate is going to be, there's a direct proportionality between the concentration and the time. And so we can use that to say, well, on a graph plotting our concentration versus time directly, if it was order 0, we would have a straight line, but it isn't. Now let's look at the last graph. I'll go to the correct one afterwards. Basically, you're looking for which one has a straight line. The last one, ln versus time, it doesn't have a straight line, it's more of a curve that represents first order. So the first order one doesn't work. The second order graph, which is the 1 over concentration versus time, does have a straight line slope. So we say that because there is proportionality between 1 over the concentration of NO2 and time. This is just a fancy way of saying because the graph shows a straight line. The reaction is second order. One thing that might help maybe is for you to write out your rate law expressions for first order, second order, and zeroth order, and then compare and see which ones have like terms. Your first order will have lns in it, your second order will have reciprocals in it. Question B says, write the rate law for the decomposition of NO2. Okay, well, let's go look up here. I see our reactants are 2NO2 forming 2NO and O2. Keep in mind that when you do consider rate laws, you only consider the reactants, not the products. And so because of that, our rate law expression is going to be simply K, our rate constant, times NO2 squared because of the 2 in front. So our rate is equal to K times NO2 squared. Simple. Alright, part C. So question I says that is the rate law described by the mechanism below shown consistent with the rate law that you wrote in part B? Justify your answer. Okay, so recall that our rate law for a rate mechanism or for a reaction mechanism has to involve only the slow step. So for our slow step, our rate is equal to, again, our K times NO2 concentration times NO2 concentration, which is equal to K times NO2 squared. Matches with original. So it is consistent. So that was just recognizing that, okay, in a reaction mechanism, it has to be the slowest step. This next one, however, is a little bit more interesting because it now involves equilibrium, which is something that you don't commonly see. The relationship between equilibrium and rate laws isn't something that's commonly tested. So once again, we consider the slow equilibrium, not the fast. Again, we want the rate determining step. And so using the slow, well, what exactly is our rate expression? Our rate is equal to K times the concentration of N2O4, right? So that's once again just using the products. Now keep in mind, however, that N2O4 is an intermediary and it cannot appear in the expression of the overall reaction. Alright, so now let's consider the fast. So considering our fast step, you don't normally do this, but in equilibrium, you have to consider both. You definitely have to consider the reversible reaction, and then you have to consider rates separately as well. And so our Kx is equal to the concentration of N2O4 over the concentration of NO2 squared. Keep in mind now that equilibrium, different from rates, does involve products and reactants. So what can we do over here? Well, I guess we can rearrange to solve for N2O4 because the concentration is identical in both expressions. So I get Kx times NO2 squared is equal to N2O4. Alright, and then if we substitute that in the original, then we get our rate is equal to K times Kx NO2 squared, right? But what is K? Well, K is just a constant. What is Kx? Kx is just a constant. So can we just combine them? So I'm going to say K prime NO2 squared. Now, if this K prime is equivalent to our original K, then yeah, it matches, and we can't disprove it. So yeah, it matches with the original. So this one was an odd question because it requires you to do some algebra to recognize that N2O4 is an intermediary, so it cannot appear in the overall rate expression, so we have to somehow eliminate it. So how can we do that? Well, we use the equilibrium statement of a previous part of the mechanism in order to fulfill that. Alright, and then now we're on to our last question. So I'm currently at 1 hour and 21 minutes. Each of these last questions were supposed to take 9 minutes, so we should have been at 69 plus 27, so about an hour 30 something, an hour 40 something. So we're making good time. I believe, yeah, an hour 30 something. So yeah, we're definitely ahead. But these last few questions are definitely much easier and much shorter as well. 7a, identify the species that was reduced in the titration reaction. Justify your answer in terms of oxidation numbers. Alright, so we're given a redox reaction. I like to write my redox reactions out completely. Plus 5, sorry, H, I'll erase that. Plus 5, H2, C2O4. Oops. Okay. Forming 10 CO2 plus 8 H2O plus 2 Mn. 2 plus, just fit it in. And then to consider the oxidation numbers of each of them, well, if you keep in mind the rules of oxidation numbers, our standard elements with a charge, or standard ions, their oxidation number is that charge. So I get plus 1. Overall, this becomes, sorry, this is still plus 1. O4, well, remember oxygen is going to be minus 2 for the majority, and that a polyatomic ion, the sum of the oxidation numbers has to add up to the charge. Now there's 4 oxygens, so I get minus 8 as that total, which means that my manganese has to be plus 7. Regarding the H2C2O4, so oxalic acid, our hydrogens are going to be plus 1, our oxygens are going to be minus 2, so I get minus 8 plus 2, and the charge is 0. So 2 minus 8 is negative 6. I need to have an oxidation number of negative 6 across 2 carbons. So each of them is going to have to be negative 3. Or sorry, positive 3. Rewrite that. Because we want to cancel the charges out. So because negative 8 plus 2 is negative 6, we want to get positive 6. So our carbons are each going to have plus 3. Now in this case for CO2, well, oxygen is minus 2, that gets a total of minus 4, so our carbon is going to be plus 4. Plus 1 and minus 2, that one's fairly straightforward, and this one is going to be plus 2, because it's just a charge. Alright, so now in terms of oxidation, remember we can use our acronyms. We can use oil rig, You can use Leoger, whichever one you want. Essentially what we find out is that oxidation equals loss of E minus. So think about what the oxidation number represents and how that relates to a loss of electrons. We want to gain an oxidation number. The question is asking us for reduction. So because our reduction is a gain of electrons, it is a loss of our oxidation number. So if you consider what exactly decreased, hydrogen has been +1 throughout, oxygen has been -2 throughout. Our carbon went from +3 to +4. That was the oxidation. That's the last term. Manganese went from +7 to +2. So there is a reduction because of a loss of because of a gain of electrons and a loss of oxidation numbers. Okay. Part B looks fairly straightforward. I'm given a burette and I'm given timestamps, initial and final, and I just have to find the readings and then the volume of KMnO4. Alright, now in this case, remember when you're reading a burette for a titration, you always consider the meniscus, so where the lowest part is, that'll give you the more accurate result. So if you look carefully over there, think about exactly where our final is. So I'll start with final because we want to find the total amount of volume changed. So our final, it looks to be between 29 and 30. It's below the 29.5 mark, but above the 29.6 mark. So I'm just going to put it as 29.55. It's in ml. My initial, it's above the 3.5 mark. It's also above the 3.4 mark. So I'm going to say it's about 3.35 ml. Now keep in mind, the reason why I'm being this precise is because we were told that it's 50.0 ml. That's 3 significant digits. So we have to be this precise. And so the volume that was consumed was 26.2 ml. You could write 26.20 ml. That was, I believe, the accepted answer as well. In terms of significant digits, 26.2 is technically more accurate, but Question 7C. Given that the concentration of KMnO4 was 0.0235 molar, calculate the number of moles of MnO4 ions that completely reacted with the oxalic acid. Okay, so this is a little bit of, once again, your basic stoichiometry, if you even need to do that. This seems much simpler because KMnO4 actually will break up into the MnO4 ion. And so we just have to consider that we have, if C is equal to N over V, then N is equal to CV. So our concentration, now keep in mind KMnO4, so potassium permanganate will split up evenly into potassium and the permanganate ions on a 1-to-1 ratio. So because of that, our concentration of permanganate is still going to be the same, so it's going to be 0.0235 molar. And then we multiply this by what we found in the last question, which is 26.2 ml, so 0.0262 liters. And we get our value as being 0.000616 moles. Or if you want, because we have enough decimals in this case to justify it, you can put it in scientific notation as well. Okay, redox titrations. Part D, the student proposes to perform another titration using a 0.139 gram sample of H2C2O4, this time using a lower concentration in the burette. Would this titrant concentration be a reasonable choice to use if the student followed the same procedure and used the same equipment as before? Justify your response. Well, if you think about it, if you lower your concentration to get the same amount of moles, you need to increase your volume used. Now, if you consider 0.0235 moles going to 0.0014 moles, I'm just going to put that in my calculator. So 0.0235 divided by 0.0014, it's about 16.8 times less. Alright, so then 16.8 times our volume. So times 0.0262 gets me 0.44. So that's 440 ml, which is about 8.8 burettes. Not feasible at all. The idea of a titration is to be extremely accurate and to have concentrations such that the titration can be fulfilled within 1 burette. So we definitely do not want 8.8 burettes. This mathematical reasoning you definitely can use to prove your point, or you can just be general and say that because of the drastic decrease in concentration, the volume necessary to reach the endpoint, I would definitely use that word. So use the word endpoint. It's a good term. So use the word endpoint and say that to reach the endpoint, it's not feasible to do it within a 50 milliliter burette, thus making the titration inaccurate, and thus it's not preferred. Alright, so that marks the end of the 2019 AP Chemistry Free Response questions. Thank you so much for watching. Just put a big thank you here. Okay, you know what, I'm going to erase that. That did not go well at all. But yeah, thank you guys so much for watching. You guys have been great with your support in the comments down below. As always, remember to hit that like button if you enjoyed the video. If you learned something out of it, comment down below any suggestions you have for future videos, or any suggestions you have for how I should do my videos in the future. If there's any specific thing that you liked previously, I did change up my format so that I have the questions on the side now for you guys to see as I'm going through them. If you preferred the old format, be sure to let me know. Remember to subscribe and hit the notification bell as well so you don't miss my next video. Once again, thank you so much for watching Patel Academy, and I will see you guys next time.